Welcome to this presentation on high-performance computing. Over the course of this presentation, we will discuss the joint project between Seanodes and UCL. The project relates to Hadoop and allowing Hadoop and the ecosystem of Hadoop to leverage the inherent benefits and capabilities of the Seanodes platform. Over the course of this video, we will examine the research that our team has performed to gain a better understanding of Hadoop and the underlying components that make up Hadoop, and obviously Seanodes. The first thing we're going to examine is the purpose of the project. The purpose of the high-performance computing project is twofold. First, to determine whether it is possible to eliminate the Hadoop distributed file system's three-way mirroring mechanism, or alternatively, replace Hadoop distributed file system, or HDFS, altogether. The second goal or purpose is in the event that it is possible to eliminate HDFS's three-way mirroring and HDFS, the preference is to eliminate the entire component of HDFS. We are now going to delve into the research, and we're going to start with looking at Seanodes. The obvious question is, what is Seanodes? Seanodes is a software-based clustering product. It is software that is installed onto each server that is to be a part of a cluster. The software then takes the RAM and direct attached storage of each participating server and aggregates it into a shared volume. Finally, a file system is layered onto the volume to complete a virtualized environment. The nodes in the cluster communicate via gigabit Ethernet connections. Importantly, nodes can be added and removed from clusters without affecting the cluster's performance or availability. Now that we know what is Seanodes, the obvious next question is, what is Hadoop? Hadoop is an Apache open source software project that enables the distributed processing of large data sets across clusters of commodity servers. It is designed to scale up from a single server to thousands of machines with a very high degree of fault tolerance. Hadoop is not a software product unto itself, but rather an umbrella term that refers to an entire ecosystem of Java software packages that combine to form a framework for a large-scale, high-availability, parallelized processing of data. The core components of the ecosystem include Hadoop Common, Hadoop Distributed File System, Hadoop Yarn, and Hadoop MapReduce. We'll take a further look at Hadoop Distributed File System as it's a key component and key aspect of this project. A key and critical component of the Hadoop ecosystem is the underlying file system. In Hadoop, the de facto file system is the Hadoop Distributed File System. It allows data in a Hadoop cluster to be broken down into smaller pieces known as blocks. These blocks are then distributed throughout the cluster. This allows the MapReduce functions to be executed on smaller subsets of larger data sets. This provides the scalability that is needed for the processing of large data sets. The Hadoop Distributed File System, or HDFS, is constituted by two components. The first being a name node. The name node primarily keeps file system metadata. The second component is data nodes. Those store the actual data. Now, the HDFS system employs a three-way mirroring mechanism that essentially keeps three copies of the same dataset. The process helps in data reads and recovering from failures, but at the cost of storage space and data writes. Because of this perceived high cost, there are at least 8 ways that have surfaced to replace HDFS. We will review some of the more viable and reasonable alternatives in this presentation. Of all the alternatives available, there are at least 3 that seem to be viable. The first of those 3 is the Ceph file system. Ceph is a LGPL licensed file system that offers object, file, and block-based storage options that can be used to back Hadoop operations. Although it is important to note that block and file storage options appear to be simple wrappers around object storage. For Ceph to be used as a drop-in replacement, there are 3 requirements. 1 is a Hadoop installation. 2, a Ceph file system installation. And 3, a Ceph file system Java package. In addition to Ceph, there's also GPFS, which is an IBM product. Unlike Ceph, it is a closed source file system, but it too can back Hadoop operations. Similarly, it has 3 requirements: a Hadoop installation, a GPF installation, and a GPFS connector installation. The GPFS connector comes with the GPFS installation. The last viable option is GlusterFS. Gluster is an open source file system backed by Red Hat. It simply requires an Hadoop installation and a GlusterFS installation. All connectors and all other supporting software come bundled with the underlying file system. Conceivably, any of the previously 3 mentioned file systems can be layered on top of the storage devices Seanodes virtualizes and aggregates. While each of these prepackaged, ready-made options are viable alternatives to HDFS for Seanodes, there is yet another option, and that option is a homegrown alternative. Hadoop is capable of working with alternative distributed file systems. Essentially, there are 2 core requirements. First, the alternative file system must look like a native file system and should be able to be accessed as a local file system. Further, it should be able to tell the MapReduce layer of the Hadoop ecosystem which is the closest data location. The second requirement is that the alternative file system provide implementations of the file system class and the file context class should this file system be used with Hadoop version 2 or higher. Once the file system and file context classes have been implemented, the implementations can be tested using BigTop, a packaging and test suite that accompanies the Hadoop ecosystem. By fulfilling these requirements, one can prepare a homegrown HDFS alternative. After several weeks of intensive and rigorous research using various sources including websites, publications, and interviews, we have come to the following conclusion. First, there are at least 3 turnkey solutions that Seanodes can use as HDFS alternatives. However, should Seanodes require a more customized solutions, it is possible to develop a homegrown alternative. It is important to note that in order to develop this homegrown alternative, it will require a team that is knowledgeable about Java, the Hadoop ecosystem, and the Seanodes software platform. While this team is capable of attempting a customized alternative implementation, it will require a significant amount of time to be invested in learning the underlying Seanode system. And unfortunately, as our team is time constricted, it is most likely we will not be able to deliver a complete proof of concept, yet alone a feature-complete product. With this in mind, we have scoped our future plans. Accordingly, our future plan is to prepare a web-based dashboard for Seanodes. This is an alternative project that the client is interested in pursuing. In order to fulfill this new project, we will refine requirements with our client, and from these refined requirements, create an initial dashboard mockup. Upon approval of the mockup, we will create a feature-complete prototype, which we will then test with our clients and gain approval. With the approval, we will refactor and implement the feedback and prepare an initial release. We have now reached the end of the presentation. I thank you for your interest in the joint venture between Seanodes and UCL. Should you be interested in more information, you could find that online